Good morning, and thank you for joining us today for this webinar. My name is Darious Naylor, and I'm the Global Fiberglass Commercial Director for Engineered Products. I started with Johns Manville, affectionately known as JM, late last year. I have a background in manufacturing, sales, and retail operations previous to joining JM. Today's training is on reinforced fiberglass fundamentals and will be led by Dany De Kock. The webinar is scheduled for 1 hour, and I encourage you to ask questions via the Q&A option at the bottom of your Zoom screen. You're also free to use the chat to ask questions, and we'll have someone monitoring the chat to answer those questions within the chat as well. At the end of our call today, I will share questions and allow Dany the opportunity to answer them. If we are unable to get to your questions due to time constraints, we'll respond to those questions via email after this training. If you have any technical difficulties during the call, you can send our host, Julie, a note, and she will help work to troubleshoot those issues you are having behind the scenes. I believe most of you are familiar with JM, but before I hand it over to Dany, I will provide a brief overview of the company. Johns Manville is a global company founded in 1858 with over $3 billion in annual sales and owned by Berkshire Hathaway. We have 8,000 employees, 44 manufacturing facilities, and 5 technical centers around the world. We manufacture premium quality insulation, commercial roofing, fiberglass, and technical non-woven products. On that note, I'm very excited to have Dany walk us through this training today. Dany has studied chemical process technology and started his career at Dow Chemical in 1984, where he worked for over 20 years in different thermoplastic divisions, laboratories, production, research and development, and technical service. In the meantime, he's certified for Six Sigma Green Belt. He joined Johns Manville as European Technical Service Leader in 2005. In 2007, he took the technical support responsibility for the Duracore gypsum products in Europe and the Middle East. During the same time, he certified for Lean Six Sigma Black Belt. When Johns Manville moved in 2014 to global business units, he became the Global Application and Technical Service Manager and is still the function he currently holds. His responsibilities cover fiberglass products for gypsum and composites, as well as market position of organo sheets for the new Johns Manville business unit. Please welcome your trainer for today's webinar, Dany De Kock.
Thank you, Darius, for the nice introduction. And thank you for everybody who's on the webinar to attend and to learn what we have today to present what is glass and what is Johns Manville production about. So I don't know if it's morning, afternoon, or evening where you are, but everybody's welcome to attend. We're going to talk about 30-35 minutes about glass manufacturing. And like Darius said, you always have the possibility for Q&A or using the chat function, which will be answered by somebody else who's attending the call. So what is glass? And if you talk about glass, what do you think about? A lot of people think about tableware, a glass to drink out. Yeah, have flat glass, window glass. You have windscreens in cars, it's also glass. So container glass like bottles. So people think most of the time about that. And some guys, they think about a movie glass, but that is not the topic what we are going to talk about today. Today we're going to talk about fiberglass. And glass fiber or fiberglass, wherever you are in the world, somebody using different ways of writing it or just pronounce it differently. But I'm going to speak about fiberglass here, what we produce and how it is compared to other materials. Fiberglass has nothing to do with the optical fiber, what you can see there. Optical fiber, Johns Manville is not producing. Optical fiber is only for data transfer, and fiberglass is for composite reinforcements. If you compare it to human hair, which is in the environment of 75 micrometer, the glass fiber or the fiberglass we are producing is around 10 to 17 micron. Of course, there are other types which are a little bit lower or a little bit higher, but that's the average of our product range, what we have today. So talking about different fiberglass types, you have a lot of them. You have A-glass, alkali glass, you have alkali resistant glass, dielectric glass, ECR glass, You have S glass, it's high tensile strength glass. You have R glass with its high properties at high temperatures. You have C glass, mainly used for non-woven production. But the glass type we're going to touch today is E glass. It's electrical resistant glass. And it's mainly in a bundle. It looks like that. If you take a single end roving, it looks like the picture at the right side. So how do we manufacture glass? So there's a formulation, but the formulation is not strictly controlled very tight because we are using natural materials like clay, dolomite, silica sand, limestone, and columenite. And these products are milled into a 50 micron sized powder to form the glass fiber. And the different types of glass fiber you can see at the right side, it are single end roving, multi-end roving, or dry or wet used chop strands. And the products that we're going to touch today are mainly these three: chop strand, multi-end, and single end roving. So we start with single end roving manufacturing. So we have a furnace, the raw material storage, you have the silos. The silos are feeding a mixing unit into the right percentage, which is designed for the furnace, and also depending on the quality of the raw materials. And because it's our raw materials are from natural source, they have a complete, we need sometimes to adjust that material, these mixes or batches, as we call them, to feed the furnace, because we need some flexibility to keep the quality of the glass the same that we send to our customers. So if you look to the furnace temperatures, you need to heat them up very high. So a furnace temperature is normally between 1350 and 1400 degrees, where you melt the raw materials, where you melt the organic materials. And the refinery, when the glass is molten, and when you move further down to the positions where you pull the glass, the refinery is about 1340, 1350 degrees. The forehard, where we call that also legs, where we feed our bushings, where we feed our pulling units, there it's about 1260 degrees. It's sometimes a little bit different, but it's also not a fixed number. And a bushing, how does it look like? I will come to that. I will discuss that in detail. I will discuss the sizing application and the winding, how it's done, and the influence of winding for the properties at the customer. So winding of a single end roving, you pull from the bushing and you bring then the fibers together. And in the meantime, you put the sizing application on it, and then the winding, the bobbin is created, the direct roving is moved to an oven, and we have different, you can use different drying types. You have hot air drying, and you have also microwave drying. So both of them have pros and cons. In Johns Manville, we mainly use microwave drying or dielectrical drying. And after the bobbin is dried, there are some, we clean that to reduce the sizing migration from the outside and the inside. Once that is done, it's packed and it goes to the customer on a pallet, as you can see there. A direct roving is a single end roving. You can see that it's all the bundle is nicely together and the right picture, because it needs to be processable in a way that our customers want to use it. We have also dry use chop strands. So why dry use chop strands? In fact, we started with talking about the way how we make direct roving. In this case, you see still how the direct roving is made, but in this case, we do chop the material, we don't wind it. It's chopped under the bushing or a little bit further. You consolidate it into a kind of a rice grain free flow material. You dry it, and then you can pack it, and you can send it to the customer as such in a big bag. It looks like the picture down there. It's a free flow material, and it is bundled like I said, like a rice grain. So what else? What other type do we have? We also have multi-end roving, and multi-end roving is a complete other animal. We wind it. But the winding is not a bobbin. We wind it, we call it a cake winding. It's a little bit smaller, lighter in weight, and we dry it, separate and this drying is done in a hot air oven for a long time, like 18 hours drying time. And what do we do with these small bobbins afterwards? We call that assembling, because all these cakes do have small filaments which are bundled together, and they need to be assembled to be used at customer processes. So they are also, we produce bobbins out of it, and these bobbins are then palletized, linked together for a continuous process at our end-use customer. We are proud on sustainability in Jones Manville. We've done a lot of that the last years, and to avoid landfill, recently, the last 2 years, we have focused on reducing waste. So 97% of our own waste, and this is line-up waste, clean waste from our bobbins, what we take out, that we cannot sell to customers, we take care of it, and we have built a complete plant in our plant to recycle it. So how does it look like? So we pulverize or we make powder out of our material, just the same like we do with our raw materials. So we have that also in a 50 micron size. And because there is an organic material on it from our sizing, we have to burn that off. Also, that is done in a controlled way, that we recuperate the heat, etc., that we don't expose it to the outside. Everything is done in the most proper way and according to the latest standard of the industries. And since 1990, the fiberglass industry in total, not only Jones Manville, has done a lot to reduce the carbon footprint. They have done a reduction by 60%. And I'm going to talk on the next slide how we have done that over the last 30 years. So if we look on the fiberglass furnace, how does it look like? So the fiberglass furnace is, if you look from the inside, it looks the same as a wine cellar, a beer cellar, but we are using other materials to do that. So we are not using normal brick, we are using refractory brick, which is zirconium oxide, which is heat resistant and more or less wear resistant to the abrasive material, which is glass. It's a mortar-free, self-supporting, so you build the walls by putting the blocks of the refractory brick on top of each other, and then you make a nice hood out of it, which is self-supporting. Like the Romans did in the past with the bridges, it's exactly the same way of the self-supporting that we use for our furnaces. And when you look at the left bottom side of this slide, you see two openings. This is the feeding of our glass raw materials in the furnace. So how do we do that? We have two day bins, which are coming from the mixed materials, what we take out of the silos. And we feed at one side. Once the day bin is empty, that way we start up with another day bin at the right side, for example, just not to disturb the continuously flow what we need to have in our furnace. And the red bars, what you see in the furnace, this is gas fire that we are using to heat up the top of the glass or the raw materials, the sand in fact. And we have also these pins, what you see, all these vertical lines. This is electrodes to heat up with electricity. By doing that, we reduced already the carbon footprint from the glass production. And on top of that, we also use oxygen for oxyfire to reduce the use of gas and to reduce the carbon footprint even more. So, like I said, glass temperature, it's done, it's molten very high. It's 1350 degrees C, more or less. But the oven temperature, the top of the roof, the crown temperature, it's about 1650 degrees. So this refractory brick needs to resist high temperatures. And we cannot run a furnace up and down. When it starts to run, we need to run it for about 10 years. What is the average lifetime of a furnace? We try to do it more, of course, because when there is no damage, and the damage is most often coming from the side walls. The side walls are getting thinner all the time because of the abrasiveness from the glass fiber, taking step by step thin layers away. And when this side wall becomes too thin, then we need to have starting our rebuild. And a rebuild is planned a long time in advance. It cannot be changed a lot. So if we plan for a rebuild, like in 6 months from now, we cannot say we do it over a year because then it's not possible. A planned date is a date when we do it. And if you look to fiberglass forming, how does it look like? We pull fiber through a bushing. And a bushing, if you look like it's an expensive material, it's precious metal, what we use for that. And it has a lot of tips. The tips have a diameter of 1.5 to 2 millimeter. And that diameter is defining, together with the pool, the thickness or the diameter of the fiber, what we produce out of it. We have bushings from small bushings for low tax material, so 1,000 tips, but you have also bigger ones for 8,000 tips per bushing. So it depends on which product you make. You need to choose your bushing size and also what product you pull out of it. So fibers, like I said, are pulled at speed to achieve the required diameter. Together with the tip and the speed of pulling, you get to that 10 or 17 micrometer. So fiberglass on itself is a weak product. It will break. It's really sensitive. So we need to apply something to keep it processable at customers. So we apply that sizing. And what is sizing? It's nothing more than a film that you put around the glass, single glass filaments. In Germany, they say Schlichte. In French, they say ensimage. So this is just a film around it, and it's a protection film, but also it has a function. Sizing is applied by passing a rotating roller. And if you can, you see it in that picture or at that drawing, that rotating roller is in a sizing emulsion, and it's picking up the emulsion and bringing it over the roller in a thin film to the glass filaments. And sizing is always water-based emulsion of chemicals. Why is it always water-based? Because it's an open bath what we are using. You cannot do it in a closed way. So our operation and operation in other companies as well, if you use sizing, you want to have it water-based, otherwise you expose your plant personnel to chemicals, and this is not needed. So if you can do it as such, it's the best way. And for each polymer matrix, if it's polypropylene, polyamide, unsaturated polyester, we need to have a special sizing. You cannot use a single sizing for all. You can try to have as many polymers covered, but then you give in on properties. So normally per polymer group or polymer type, you use a specific sizing. And we developed that sizing in-house. And it's a matter of long time trial and error because it's not easy to develop a sizing like in 6 months. It has to be its trial and error in many cases. And sizing is applied before the single filaments are gathered into a strand. And you will see on the next slide how that is done. So this is in reality how it looks like. You see the operator, he's lining up on the picture, he's lining up the filaments coming from the bushing, and he's bringing them over the sizing applicator, and he then will put them in a gathering shoe that they are bundled again, and that winding can take place. So we need to cool the material because bushings are very hot. They are over 1,000 degrees, 1,100 degrees. And how do we cool that fiber? Because we pull at very high speeds. And with very high speeds, I mean super high speeds. It's not really that you can follow what is happening. In 0.3 seconds from the bushing until the winder, we need to cool down from 1,000 degrees up to around 50 degrees or lower. And in the meantime, we need to apply the sizing that the product is usable for customer needs. So cooling is done with ventilation, with air, but also with water spray. And the water spray is done in such a fine way that it has the highest effect to take the heat out. And this is also explaining why we are using for our sizing, the emulsion, it's also water-based, because if we do it that way, there is no effect of interference of the different materials. So fiber strands to the winder or chopped are pulled at more than 1,000 meters per minute, which is very fast. So we go on with fiberglass winding, but if we go for a bobbin, and bobbins or single end roving materials, the winding pattern is influencing a lot. We need to look for the right pattern, or the cross ratio, how we call it, because it's depending on the dryer type and the drying efficiency. It needs to be more open, more closed. It's all done in controlled by the winding. Also, the unwinding is important. So customers are unwinding, but we need to define how the unwinding will take place. And I will come back later on the next slides what the possibilities are. So we want to have flat top and bottom flange of the row of the bobbins, and it normally doesn't have a big effect on the quality, but we want to pack them. So we want to have that the bobbin can stand on a platform or a pallet and be stacked together, that we can ship it in a nice way. If it would not be flat, if we would have like a conical top, we could not put 3 or 4 bobbins above each other and ship them as such. So the repeating turning points, so the way you wind from left to right, are very important, because they will have an influence for the use at the customer as well. The strand width is important. You can have a round strand, you can more have a flat strand. It depends on the process, the end-use process, what is the best. Not every type can be wound in the same way. So depending on the sizing, depending on the drying, you will have to choose the strand width that can be applied. And what is also important, the interstrand adhesion, because you can, when you dry your material and you wind, you can pack it so hard that all the strands stick together, but then it's not usable at the customer. So customers want to use it, that they take it out layer by layer without any problem. And if you look to the winding pattern, if the winding pattern is not correct, it can cause collapsing of the bobbin. In the right side of the picture below, you see a deformed bobbin, which can cause issues at customers, because when they start pulling out the roving, it collapses, it creates a bird nest, and they have to stop the process because the fiber is breaking, or the bird nest is blocking further pull through their systems. Sizing can also influence the color, although most of the time color has no influence on the quality of the product. It is, fiber needs to be white. The industry wants to have white fiber, and maybe it could be better that sometimes we have a little bit more brown, that the properties would be better, but it's an industry standard and we have to follow that way. So looking to the fiberglass winding in reality, you can have single bobbin winding or double bobbin winding like you see here. And it's you see it going from left to right, and vice versa. So this is always the winding pattern, which is defined by this way of producing the winder, the bobbin. So if we look to fiberglass design for unwinding, we can do whatever we want, but at the end, it's the customer who needs to run the product. So most of the time, unwinding is done from the internal. And why do they do it? It's free. You can go to high speeds. There is no tension on it. It's really very simple to do. And bobbin stays in the packaging film. You can put it on a platform, a grill rack, in vertical way like it stands there, and you just pull all the bobbins out from the inside. It's a cheap solution. It's easy handling. You can even put it from a pallet if you have linked material. But the downside is you always have a strand twist. Because of the winding pattern from left to right, you always have a twist. And the twist is more from the inside, you have more twist than when you go to the outside. But like any industry, there are solutions for compensating for strand twist. You can put your bobbin on a rotating platform, which is going the other direction than we were winding. So then you compensate for twists. You will not take them out completely, but you will reduce them drastically. When we talk about tapes, and tapes were mainly starting with carbon fiber. And since glass fiber is getting introduced in tapes as well, you see that people want to pull from the outside. And you can, if you pull from the outside, you have no twist at all. So you can pull each fiber without any problem. It's ideal, like I said, for UD tapes. And it has also a downside because it's glass on glass unwinding what you have. And we talked about in the furnace that glass is abrasive. So when you do the unwinding glass on glass and you don't have your line set up well, you could have some damage that you start creating dust, or even in worst cases, fuzz from the outside unwinding. It's more complex because the creel arrangement needs to be done. So you need to, in that horizontal way, you need to position all the bobbins. And as the bobbins do not have a core, they are not like carbon fiber that they are wound on a cardboard core. The inner side is always different in diameter. It's not a lot, but you need to have an expandable fixture that you can adjust for each single bobbin. And if you do it that way, you need to handle all your bobbins to put them on a creel and to be unwind. And bobbins are around 20 kilos of each. So I can tell you it's a lot of weight in an operation needs to handle to get that positioned on a creel rack and have it lined up for producing tapes. You also need the braking system, because if you have external unwinding and you would not have a brake, if you stop your line, the bobbin would continue to unwind and you would create a problem in on your line. Also, a difficulty, every bobbin is packed in a film, and the film is to protect the fiber for transport, but also for use at customers. And you need to, for outside unwinding, you need to remove that film. So you need to do it very carefully, because when you cut the fiber on the bobbin, it can have an effect which is for few meters or even a lot of meters continuing, because it looks a fine cut, but it could get you in trouble for a longer period when you run the material. So we try to develop glass for several processes. And if I look to it, polypropylene is a widely used material in the industry. It's a leading material these days for different applications for continuous processing. And you can make granulate LFT out of it. But we need to also work with the same material that we have direct LFT, for example. It's another process, but it needs to work there as well. Or injection molding compounder, where you have a compounding unit on top of an injection molding machine. And the latest technology, for example, from Arberg, with fiber direct compounding, where they chop the material into this directly before the screw and put it in the melt on an almost standard injection molding machine, is quite challenging job for the roving, that it needs to work for that one as well. Of course, there are a lot of other applications what are used. We have GMT, glass mat technology, thermoplastic. You can chop direct roving as well. And there we want to avoid that the roving is static, that it's not sticking to the sides of the cutting unit. For tapes, we touched that before. And of course, organosheet. Organosheet is using a non-crimp fabric or a woven fabric. So the roving needs to work in these kind of processes as well. And if you count all these types together, a customer can use any process they want, or make combinations of it and use one single type of material which suits all these processes. So it's the same for the fiberglass sizing development. So again, I chose polypropylene. It could have been polyamide, it could have been polyester, whatever. But we chose polypropylene because polypropylene is a nice material. It's used a lot, and we are always looking for technical performance. Product performance is the key. So we want high mechanical properties. We want not to have that we give in on mechanical properties by improving another part of the product, which is important for processing, for example. So we always want lowest possible volatile organic content. And why is that important? If you are in a car, for example, you don't want the car to stink like it was doing 30, 40 years ago, that you were smelling, oh, this is a new car. These days it's over. You want to have no smell. A car needs to be neutral, or the car interior needs to be neutral from smell. We want to have heat stability, so no discoloration. We want to have a white product. And think about white goods, washing machines, for example. If you reinforce that, white, the white material, what is normally in a washing machine, we want to keep it white. The glass should not have an influence on the color, a visible influence on the color. And sometimes we are asked for food and drinking water approval. Also, the process productivity. What do we need to do here? Well, we want to have, if it's a roving, we want to have easy spreading and fast wet out. Independent what process it is, we want to have, the customer wants to have every single filament impregnated with the material for end use. They will know. We try to provide give zero filament breaks, which lead to fuss. Although every contact point that you have in your process, in the customer process, can lead to problems. So we want to avoid that with building in protection in our sizing development. Customers want sometimes easy splicing because they have a continuous process. So splicing needs to be possible, because if you make a very fluffy fiber, splicing will be very difficult. So you need to find always the best possible way to compensate for all these different issues what customers could have. And high-speed pull-out with equal tension and bobbin stability until the last layer is also important. Nobody wants that they need to throw away like 10 kilo of a bobbin, so it needs to run out until the last layer, that there is no waste created. And like I said, we want to have one product for all the processes. Any process, what is in the industry, for a type of end matrix use, we want to work it in that way that everybody can use the same material, because you only need one release for this material and then you can apply it for everything. So for the tapes, this is something different, and the weaving is a little bit different. You want to have uniform strand width, and because you want to have your fabric flat and nicely distributed fibers, that you have a nice woven material. And tapes, for example, you want to have them opening as far as possible to have the widest possible strand width and the thinnest possible film that you can put on it to get the highest glass content possible in your tape. So our goal is always develop a product that works for all processes and meets all requirements. So we come to the fiberglass sizing composition, and this is mainly, there are two groups for that. It's coupling to the polymer, and we want protection of the fiber during the process. Coupling agents are mainly silanes to the glass, and we have other coupling agents which are bonding to the resin. So we have film formers, and a film former is a protection film. It goes around the strand, it gets it at the outside, and it makes the strand integrity. And also it protects in the process of the customer, but also in our process during our drying. We want lubricants, and lubricants needs to go to the outside as well, because lubricants avoid that the friction is getting too high in customer processes, that you create filament break and that you create fuss and stops during the process. It needs to be continuous with the lowest possible impact. And of course, we use emulsifiers, because I talked about that sizing is a water-based material. And if you have ingredients in there which are based on an organic or anorganic materials, they should be kept in the same mix in that sizing, which is put on the glass. They needs to be staying in that water material, that they don't sink to the bottom of where the applicator roller is picking up the sizing and brings it on the glass. So emulsifiers making film formers and lubricants water compatible, even if they are oil-based. So Jones Manville is mainly producing 3 different products, and the Thermoflow is our dry use substance. It's mainly for compounding, but we have also some thermoset material substance for bulk mold compound or phenolics. And even though it's in wet processes, we have also 2 products. We use them a lot to sell in the gypsum world for the fire rating, for the fire improvement. And we sell them internally or to customers for non-woven production. Our star of is our single end roving. And for that, we touched that already. We can use it for LFT, direct LFT, tape, organo sheet, and so on. And we also have that for different polymer types. For the more traditional processes like pultrusion, weaving, and filament binding, which are still mainly thermoset applications, we also have the materials, but also for the newcomer in that, it's a thermoplastic material from, it's an MMA. We have the material developed that it can be used in these processes. Multistar is our.
So thank you, Dany, for leading the training today on fiberglass, reinforced fiberglass fundamentals. Very value added. We really appreciate it. For those of you in attendance, you see my contact information as well as Dany's down at the bottom. So if you have any questions, feel free to reach out to either of us so we can get you some responses to anything that was not touched on here in the training. So going forward, we will be hosting another webinar here on May 10th. The webinar will be on the benefits of fiberglass mat versus cellulose paper in construction, and will be hosted by Tom and Rui. And if you are able to attend, we would love to have you and encourage you to share the date and topic for the next webinar with any coworkers or colleagues that you believe may be interested. This recording actually will be sent out to the team in a couple of days and the participants as well. So you'll have this information to be able to scan the QR code or use the website to register. We thank you for taking the time today to participate in this training. On that note, we will come to a close and have a great rest of your week and a great day.
Thank you, Darius.
Thank you. And
thank you for all the attendees to this webinar. You have our contact details. Don't hesitate to ask questions. You can have set up a Teams meeting or just have a phone call. Whatever is needed, I will do my best to support you the best possible way.